Welcome back to the Deep Dive, where we take complex theoretical structures, the kind that underpin everything from logistics planning to social networks, and distill them into crystal clear insights for you. Today, we are going deep, deep into the foundational mathematics of computer science, graph theory.
We are. And our focus today is really on structure and algorithm. We have two core missions, and the contrast between them is, I think, really striking. First, we're going to tackle optimization, the mathematically difficult, often intractable challenge of finding, the perfect match or the optimal pairing.
Okay, the hard stuff first.
The hard stuff first. And then second, we switch gears entirely to traversal, the surprisingly simple challenge of finding the perfect route through an existing network.
It's a journey of structural enlightenment, really. We're moving from a problem like trying to pair up thousands of potential collaborators, which sounds like a total nightmare,
It can be.
to proving the existence of a single, elegant path that hits every single connection. The structure of the problem itself determines how hard it is.
That's exactly it. Our mission is to find the simplicity hidden in the complexity or to understand why the complexity is even there in the first place.
And we'll be connecting the optimization side, which you called matchings, with its verification challenge, and then contrasting all that with these beautifully simple conditions that govern perfect routes.
Precisely. We'll be looking at matchings versus Euler tours.
All right, let's dive into the hard part then. Matchings. I feel like whenever you see a network, a set of servers, a group of people, cities needing connections, and you have to pair things up efficiently, you're looking at a matching problem.
You are. It's absolutely fundamental to resource allocation. And think of forming two-person study groups from a university class, or assigning incoming processing jobs to available server cores. You're always constrained by the existing connections. Who can work with whom, or which server can handle which type of job. Hashtag tag 1.1 defining the match. So we have to start with the rigorous definition of the thing we're trying to maximize. A matching, we'll call it $, is defined simply as a subset of the graph's edges, where no two edges share a common node.
So if you picture the graph and you color the chosen edges red.
Exactly. If you color them red, it just means no two red lines can touch each other. They have to be completely disjoint.
And that constraint, that's where all the difficulty comes from, right? Because in the real world, connections often conflict. You can't have two people trying to partner with the same single resource.
Precisely. When we talk about finding connections, what we're really talking about is maximizing independence.
Which leads us straight to the core objective, the maximum matching problem.
Right. We're seeking a matching that contains the absolute maximum number of edges possible. We want to form as many independent pairs as we can.
And the ideal state, the sort of nirvana here, is a perfect matching.
A perfect matching. That's where every single node in the entire network has found a partner. Nobody is left out. No singles.
Okay, and there's a really obvious ceiling on this, right?
Yeah, a very trivial, common sense ceiling. The simplest observation is that any matching can have at most half as many edges as there are nodes. If you have 100 people, you can only create a maximum of 50 pairs. That's the absolute upper bound.
But if that upper bound is so obvious, just half the population, what's the least intuitive part that trips people up?
It's the sheer combinatorial explosion. It's about finding which specific 50 edges out of potentially thousands of possible connections actually form that maximum set. It's not the number of pairs that's hard to predict. It's which pairings satisfy that non-touching rule all at the same time across the entire graph.
So the geometry of the network itself can make that simple 50-pair goal impossible to reach.
Exactly. The structure often makes the trivial bound unattainable.
Yeah.
Okay, so let's say we start with just some arbitrary matching. Maybe a few pairs we found easily. How do we grow it? We need some kind of mechanism for improvement.
And that's where we start looking for the leftovers, the nodes that missed out on that first round.
Exactly. We define an M-exposed node as a node that has no edge attached to it in our current matching.
They're the singles.
They're the singles, and they are our target for growth. Now, the method for this growth revolves around paths that interact with the current pairing in a special way. We call this an M-alternating path.
An alternating path. It sounds like a zebra stripe of connections.
It is. That's a great way to think about it.
Yeah.
It's a path where the edges strictly alternate.
Yeah.
One edge from our matching nuller, then one edge that does not nuller, then one in nuller, then one not in nuller.
Committed, available, committed, available.
Exactly. So we have our singles,
Yeah.
and we have this zebra stripe path. The action happens when we combine them into what's called an M-augmenting path.
Okay, this sounds like the key.
This is the revolutionary structure. An M-augmenting path is an alternating path that starts at one M exposed node, a single, and ends at another M exposed node,
A different single.
a different single. That's a single-to-single alternating path.
Okay, why does starting and ending with a single make all the difference?
Because of the brilliant flip operation. Think about the number of edges along this path. Since it starts with an edge that's not in the matching, and it ends with an edge that's not in the matching.
Right, because the endpoints are single.
The path must necessarily contain exactly one more non-matching edge than matching edges.
It's an odd number of edges total, and the available ones outnumber the committed ones.
Precisely. So if we find this structure, we execute the flip, we take all the edges on that path that were in our matching, and we remove them. And we take all the edges on the path that were not in our matching, and we add them.
You just swap their status along that one specific path.
You swap their status, and the result is beautiful. The matching rules are still followed, no two edges touch, but you've now brought two previously single nodes into the matching. The total size of your matching, $, increases by exactly 1.
It's like a perfect atomic growth engine. You don't have to tear down the whole thing. You just find this one little chain reaction that lets you pull in two more singles and grow the matching by 1.
That is the foundation of all maximum matching algorithms. You just repeatedly search for an augmenting path, you flip it, and you continue until no such path can be found.
Which brings us to the moment of truth. If the augmenting path is the engine for growth, then the absence of that engine must mean we're done. We've hit the maximum.
And that is the core insight of Burge's lemma. It provides this elegant, foundational proof of optimality. It states that a matching dollars is maximal. It has the maximum possible number of edges, if and only if there is no M augmenting path.
That if and only if is huge. It's not just a one-way street. The structure perfectly mirrors the property.
Exactly. We use the path to find the solution, and the lack of the path to prove the solution is complete.
Okay, so one direction of the proof seems pretty easy. If an augmenting path exists, you just showed we can make the matching bigger, so it wasn't maximal.
That's the easy direction. The harder direction is the really deep structural insight, proving that if dollars is maximal, you absolutely cannot find any other matching, let's call it $, that's bigger.
And this is where we have to do that complex mathematical comparison, looking at the differences between the two.
We analyze what's called the symmetric difference. Imagine you have your matching dollars and this hypothetical bigger matching dollars. You overlay them. The symmetric difference is just the set of edges that are in one but not the other.
So just the disagreements between them.
Just the disagreements. And that resulting graph, the graph of disagreements, can only be made of two things: alternating cycles and alternating paths.
Why only cycles and paths?
Because in any matching, every node has at most one edge touching it. So when you combine two matchings, any given node in this new difference graph can have a degree of 0, 1, or 2. And any graph where all nodes have degree 2 or less has to be just a collection of disjoint paths and cycles.
Ah, I see. And because we started by assuming the dollars was bigger than dollars, the components of this difference graph have to be unbalanced in favor of no.
Exactly. If $, is greater than $, there must be at least one path component in that symmetric difference that has more edges from never than from never. And a path that starts and ends with a $, edge and alternates means its endpoints must have been
That exposed. They must have been single with respect to the original smaller matching $.
You got it. So the very existence of a hypothetical larger matching dollars immediately implies the existence of an M-augmenting path for $. It's a beautiful proof by contradiction.
It shows that structure defines optimality. It's not just a hunch. It gives us the whole algorithm blueprint. Start with nothing, find a path, flip it, repeat until you can't find any more paths.
And then you're done. But, and this is the big caveat, the critical part, where the real complexity of graph theory hides.
The search itself.
The search itself. The algorithm just says, search for an M-augmenting path. It doesn't say how. And that search is not always easy.
I'm guessing this is where the structure of the graph really matters.
It matters immensely. When the graph is highly structured, specifically if it's bipartite, which we'll get to, the search is, relatively straightforward. It's efficient. But in general graphs, you can have odd cycles.
Like a triangle.
Like a triangle or a pentagon. And these odd cycles become an algorithmic nightmare. The simple alternating path search can get stuck in a loop inside one of these cycles, and it doesn't help you find a path from one single to another.
So it sabotages the search.
It completely sabotages the simple search.
Yeah.
To handle these, you have to use highly specialized techniques involving what are famously known as blossoms. The algorithm has to be smart enough to find these odd cycles, sort of shrink them down into a single supernode, continue the search, and then expand it back out. It's a whole extra layer of complexity
Yeah.
developed by Jack Edmonds. And the fact that we need this entire separate structure, the blossom, just to handle odd cycles, really highlights why the general matching problem is so hard.
Okay, so since finding the maximal matching can get that complicated with blossoms and everything, let's pivot to verification. Is there a faster way to prove our matching is maximal without running that whole exhaustive search?
Yes, we use a really powerful technique called duality. It connects our problem of maximizing independent connections to a totally different problem, minimizing covering resources. This starts with the concept of a vertex cover. We'll call it dollar.
Okay, define that for us again.
A vertex cover is a set of nodes, not edges, nodes, such that every single edge in the entire graph has at least one of its endpoints in that set. You're trying to pick the smallest possible group of nodes that touch or cover all the connections.
So we have these two competing goals. One is to find the biggest set of disjoint edges, which is the maximum matching, dollar.
Right.
And the other is to find the smallest set of covering nodes, the minimum vertex cover, dollar, dollar.
And the relationship between them is what we call weak duality. It's a simple universal rule. The size of any matching is always less than or equal to the size of any vertex cover. In notation, little dollar.
Always, regardless of the graph.
Always. The proof is so elegant because it just relies on the definition of a matching. Think about it. Take a matching dollar. It has, let's say, totally separate edges.
Okay, red lines that don't touch.
Right. Now, every single one of those dollar edges has to be covered by the vertex cover dollars. Since none of those edges share a node, to cover all dollars of them, you need at least
100 different nodes, one for each edge at a minimum.
at a minimum. Therefore, the size of your vertex covered total dollars has to be at least colors, which is the size of your matching.
So the two problems inherently bound each other. The max matching size can never be more than the min vertex cover size.
And this gives us that tremendous aha moment for verification. We call it a certificate of optimality. Imagine you're solving a job pairing problem. You find a matching of size 10, and then separately, your colleague finds a vertex cover of size 10.
You're done instantly.
You're instantly done. You know your matching is maximal because it can't be bigger than 10, and you know their vertex cover is minimal because it can't be smaller than 10.
So you don't have to search for every possible augmenting path anymore. You just have to find this other thing, the dual, and show they're equal. That's a huge computational shortcut.
It's the gold standard in theoretical computer science. Finding a solution is one thing. Finding a structurally guaranteed proof that your solution is the best possible is often much harder, and duality is the tool for that. Hashtag tag 1.5 strong duality and the marriage bottleneck.
Now, we did note that this weak duality isn't always a perfect equality. There can be a gap, and the source material pointed to that odd cycle again.
The simple triangle is the perfect example. The maximum matching size is just one. You can only pick one edge.
Right.
But to cover all three edges of the triangle, you need at least two nodes for a minimum vertex cover. So here, one is less than two. There's a gap. That gap shows a failure of the general structure to be, perfectly self-regulating.
So where does the order return? Where does that gap vanish?
In bipartite graphs, these are the nice orderly graphs we mentioned. The nodes can be cleanly split into two sets, let's say V1 and V2, and all the connections run strictly between the sets.
Like workers and jobs, or students and courses. No connections happen just between workers or just between jobs.
Exactly. And that clean division makes it impossible to form an odd cycle. You can't have a triangle in a bipartite graph.
And without the odd cycles, the structure becomes orderly enough to guarantee perfection.
That's Koning's theorem. It states that in a bipartite graph, the size of the maximum matching is exactly equal to the size of the minimum vertex cover. Strong duality holds.
So the optimization problem and the verification problem become perfectly equivalent. The bottleneck to pairing is the same as the minimum thing needed to cover all pairs.
Beautifully put. And this brings us to probably the most famous application of this idea, Hall's marriage theorem. This looks specifically at when a perfect matching is possible.
Right, the classic analogy of pairing people up. You've got one group, say job applicants, and another group, job slots. When can everyone get a job?
And the condition is all about structural integrity. It's called the Hall condition, it says. For any subset of people you pick from the first group, let's call it 6 overs.
Any group of applicants.
The set of jobs they are collectively qualified for, which we call Sornags, has to be at least as large as the number of people you picked. So, no Yix-Sexers.
This is basically a check against a bottleneck.
It's an inescapable bottleneck check. Imagine you have 5 specific courses, and between them, they only rely on a pool of 4 unique professors who can teach them. It is mathematically impossible to schedule all 5 courses at the same time.
Even if there are hundreds of other professors and courses in the university, that one little subset creates the fatal bottleneck.
Exactly, and the real power of Hall's theorem, which the sources note, is the certificate it provides. To prove that a perfect matching doesn't exist, you don't have to check billions of possibilities.
You just have to find that one small group of 5 courses that only have 4 teachers between them.
And that's your instant, undeniable negative certificate. In a world full of hard problems, having an efficient test to prove impossibility is incredibly valuable.
And the final conclusion is, for 2 sets of equal size, a perfect matching exists if and only if that Hall condition is met everywhere. A clean, decisive test.
Possible only because the bipartite structure prevents the chaos of those odd cycles.
Okay, so we've established that finding optimal pairings is hard. It needs complex searches, dual problems, special techniques for chaos. Now let's look at its simpler cousin, the routing problem.
Yes, a complete transition. We're moving from optimizing connections to optimizing a road. And the difference in difficulty is maybe the most famous divide in all of computer science.
On one side, we have the infamous traveling salesman problem. The goal is to visit every node, every city exactly once.
And this is notoriously difficult. It's NP complete. It scales so badly that it can bring the world's fastest supercomputers to their knees if the network gets big enough.
But on the other side, we have the postman problem, finding an Euler tour. The goal here is to traverse every edge, every street exactly once.
And this one is surprisingly simple. The moment you define the problem as traversing connections instead of visiting points, almost all the complexity vanishes.
And this goes all the way back to Leonhard Euler and the famous Königsberg Bridge problem.
It does. He realized the problem of crossing all 7 bridges exactly once wasn't about the specific layout of the town, but the structural property of the connections themselves.
Okay, so let's nail the definitions. There's an Euler path.
An Euler path starts somewhere, traverses all the edges, and ends somewhere else.
And an Euler tour.
An Euler tour is a closed loop. It starts somewhere, traverses all the edges, and ends up exactly where it started. And we're usually aiming for that closed loop. Hashtag tag 2.2, the simple condition for closure. So why is the postman problem so simple? It all comes down to a property called parity, just whether a number is even or odd.
The logic seems very basic. For a closed loop, every time you walk into an intersection, you have to be able to walk out of it.
That's it. At every single node, the number of edges you use to enter it must equal the number of edges you use to exit, which means the total number of edges connected to that node, its degree, must be an even number.
And that's the whole key.
That is the entire key. It's codified in Euler's rule. A connected graph has a closed Euler tour if and only if every single node has an even degree.
Wow. So unlike the matching problem with its complex search, here the test is just counting.
Just counting. If the graph is connected, you just go to every node and check its degree. If they're all even, a tour is guaranteed to exist. If even one node has an odd degree, a closed tour is impossible.
Why is the traveling salesman so hard then? It feels so similar.
The constraint is the difference. The salesman has to avoid revisiting nodes. That forces these rigid paths and long jumps and complex decisions. The Euler tour is only constrained by the edges. You can revisit a node as many times as you want. And that freedom is what the even degree property guarantees. It ensures that every time you enter a node, there's always an unused exit route waiting for you, so you never get stuck.
What about the open path, where the start isn't the end?
For an open Euler path, you're allowed to have exactly 2 nodes with an odd degree.
The start and the end.
The start and the end. Because at the start, you just leave once without ever entering. And at the end, you enter once without ever leaving. Every node in between still has to act as a simple transit point, so they must all have even degrees.
So 0 odd degree nodes means a closed tour. Exactly 2 odd degree nodes means an open path.
And any other number 4, 6, any other odd number of them means no Euler traversal is possible at all. It's that simple.
Okay, so knowing a tour exists is one thing, but how do we actually find it? The source mentions Hierholzer's algorithm, the onion peel principle.
Yes, and the problem-solving philosophy here is just brilliant because it totally leans into the guarantee of the even degree condition.
The guarantee that you can always leave a node if you enter it.
Which means any simple walk you take has to eventually lead back to where you started. So, step 1, start at any node and just start walking along unused edges. You are guaranteed to eventually get back to your starting point, completing a circle.
But that circle might not use all the edges in the graph.
It probably won't. So now we're in the stitch and glue phase. If there are unused edges left, the graph's connectivity guarantees that there must be a node on the circle you just made that still has unused edges attached to it.
Okay, so we find that junction point, and instead of starting over, we just pause our main route and take a detour.
You take a detour, a new excursion. You start from that junction node, and you follow its unused edges. And because the remaining subgraph still has the even degree property,
You're guaranteed to make another smaller circle.
you're guaranteed to make another circle, another layer of the onion. Then you just glue or insert that small circle right into the bigger path where you left off.
And you just keep doing that. Find a node on the current path with unused edges, make a little circle excursion, and stitch it back in.
You repeat that until every single edge in the graph has been used up.
The efficiency of that seems incredible. It's such a sharp contrast to the computational pain of the matching algorithms.
Absolutely.
Yep.
The complexity is linear. It runs in time proportional to the number of nodes plus edges. Even a massive network with billions of connections can be solved almost instantly. The structure of even degrees makes the solution trivial, guaranteed, and lightning fast. Hashtag tag outro.
This deep dive really presented a powerful contrast in difficulty. We started with maximum matchings, a really tough optimization challenge where growth depends on finding that one subtle, single-to-single augmenting path.
A path that allows you to do the edge flip and increase the matching size by 1. And we learned that general graphs are hard because of those odd cycles, which force complex workarounds like the blossom search.
Then we saw the stabilizing power of duality, the idea that the matching size is always less than or equal to the vertex cover size.
An inequality that becomes a perfect equality in those orderly bipartite graphs, thanks to Koenig's theorem. Which means that bottlenecks, which we can check for quickly using Hall's condition, are the only thing that can stop a perfect pairing.
And then finally, we pivoted to Euler tours, the effortless traversal problem. And here, the entire solution was dictated by parity.
A perfect closed route exists if and only if every single node has an even degree.
The contrast is definitive. For maximizing pairs, bottlenecks are the enemy. For traversing routes, structural parity is the key.
Right, and the critical thinking application for you is clear. The next time you face a network problem, whether it's assigning resources or planning logistics, you have to ask first, is this a difficult, complex traveling salesman problem that needs heavy optimization?
Or is this a simple postman problem solvable just by checking a basic property like degree parity?
The lesson is that complexity isn't arbitrary, it's structural. The sources highlighted that the orderliness of bipartite graphs is what guarantees strong duality. It makes a hard problem manageable.
Which leads to our final thought for you to explore. In the real-world scheduling, cloud computing, social networks, these systems often look messy and complicated.
They do. But how many of these seemingly complex challenges could be solved dramatically more simply if we could just identify an underlying, maybe hidden, bipartite structure within them? Finding that hidden structural order is often the biggest win in algorithmic problem solving. It can turn a seemingly impossible NP-hard task into a simple, efficient guarantee.